Thanks a lot, and thanks a lot for the opportunity to present this. This is still very much work in progress, so any comments that people have are very much encouraged and welcome. So I'm going to be talking about kind of what happens when we look at the natural properties debate that's familiar from contemporary metaphysics, and try and take seriously the idea that physics is supposed to tell us something about what natural properties actually are. So there's this sort of familiar, well-entrenched distinction that's arisen in contemporary metaphysics, basically starting with David Lewis, where we think that some properties are more natural than others, or more joint carving. They do a better job of carving the world up along its sort of metaphysically privileged joints. So standard example of this distinction, we think that the property of being an electron is somehow more natural than the property of being either an electron or a cow. The reason being that being an electron seems to be a really, it's a way of carving the world up that carves very closely at the joints, whereas being either an electron or a cow is a property that's more gerrymandered and more arbitrary, and less fundamentally significant. Now, it's generally said in discussions about naturalness that physics is somehow supposed to inform us about naturalness. So we see David Lewis saying that physics proposes inventories of the natural properties instantiated in our world. We see David Armstrong saying that he looks for the genuine universals, so the natural properties, in the fundamental notions of physics. And more recently, we see Ted Sider saying that the physical description of reality is objectively privileged, physical notions carve at the joints. So it seems like there's kind of fairly strong agreement among naturalist theorists that physics is supposed to tell us about what the natural properties are. Now, metaphysicians enlist naturalness to fill a wide range of different roles across different settings. So naturalness is used in various discussions of laws of nature, mereological duplication, reference magnetism, objective similarity and dissimilarity, and all sorts of other things like that. But metaphysicians don't generally tell us which properties actually are the most natural ones, or even which properties contemporary physics recommends as the best candidates for highly natural properties. So there's work to be done. The aim of this talk is first to do some groundwork to determine what such a recommendation actually requires. So what would a physical theory need to do in order to be able to provide a recommendation about what the natural properties are? And then, with this in place, to then carry out a kind of case study by examining the content of quantum mechanics in particular, and to try and locate which properties quantum theory recommends as the more natural ones. Okay, so that's roughly what we're going to try and do. So to begin, for a physical theory to recommend some hypothesis about what the most natural properties are, that theory has to provide its own kind of internal ranking about which of the properties it posits are most natural by its own lights. What do I mean by this? Well, if we want to think of the world as having this sort of metaphysical structure according to which some of the properties in it are more natural than others, and we want to think that physics can somehow tell us what that ranking is, then it needs to be the case that if we get really lucky and we end up with a fully comprehensive physical theory that's perfectly exact, fully tells us about all the truths of the physical world, that it would then have something to say about what the natural properties are. If we end up in a situation where we have like a complete physical theory and it doesn't tell us anything about naturalness, then we can't use it to figure out what the natural properties are. So in order for physics to tell us about naturalness, physical theories have to make recommendations about naturalness. They have to carry their own internal rankings. So I'm going to call the ranking among properties fixed by the structure of the world metaphysical naturalness, and I'm going to distinguish this from what I will call physical naturalness. Physical naturalness being the relevant ranking that's indexed to a particular body of physical theory. So physical naturalness is going to be a notion that's supplied by the structure of a physical theory. And there's a question about whether or not physical naturalness, according to some theory, lines up with metaphysical naturalness. In general, if we have an incomplete theory, a theory that doesn't succeed at fully circumscribing all the facts about the world, we shouldn't think that its internal physical ranking, its physical naturalist ranking, will be the metaphysical naturalist ranking. But nevertheless, for physics to tell us what metaphysical naturalness is, we need some kind of physical naturalist ranking internal to our physical theories. So the claim that physics informs us about naturalness ends up being a claim that as our physics becomes more comprehensive and more exact and better at predicting things, the physical naturalness rankings of our best theories thereby converge on the metaphysical naturalist ranking. So that's basically what's at issue when people say that physics tells us about naturalness. Now, there's lots of reasons to be skeptical of this kind of convergence. I won't go through the various arguments right now, but I'm just going to flag that there are, I think, a lot of compelling reasons to think that it's somewhat suspicious to expect this kind of convergence out of our physical theories. But even the people that are skeptical of this convergence, who take seriously the idea that there is an intelligible notion of naturalness to be had, nevertheless think that the sort of ranking among properties given to us by our theories plays an important theoretical role. So people that think, for example, that there are best systems accounts of laws of nature related reasons to think that this convergence won't happen, say, well, our account of laws of nature should not be talking about metaphysically natural properties, but rather the ones that appear in our scientific theories, the more scientifically natural properties. So even the people who think this kind of convergence picture is mistaken or misguided, nevertheless take it to be the case that scientific theories and physical theories in particular have this kind of naturalness structure. Okay, so we want to then find a notion internal to a physical theory of naturalness that can kind of mimic metaphysical naturalness in such a way that if our theory is fully comprehensive, we can think that the naturalness ranking that it provides us with will track the metaphysical ranking among properties. So first we need to know what sorts of roles metaphysical naturalness plays, so we can figure out what the analog roles the sort of corresponding physical naturalness rankings must play as well. Now, it's generally assumed that metaphysical naturalness fills sort of a family of interrelated roles. People don't generally define metaphysical naturalness, but fills some roles. For example, the more metaphysically natural a property is, the more it makes for objective similarity and dissimilarity. This is a standard condition. Similarly, people generally think that everything supervenes on the metaphysically natural properties, the most metaphysically natural properties. So you can't change a state of affairs without changing which of the most metaphysically natural properties it instantiates or are instantiated in it. There's also conditions imposed on the laws of nature. So people say that the laws of nature should only refer to the most metaphysically natural properties, perhaps when articulated in the most structural language and so on. There's various clauses that one might want to add to this. And finally, it's usually thought that naturalness has to have a kind of minimality condition imposed on it. So we don't want this proliferation of redundancy among highly natural properties. We want the most natural properties to be, the only ones that are strictly necessary for filling all the relevant roles. Okay, so if we take metaphysical naturalness to be a ranking among properties that fills these various roles, what must we think physical naturalness does? Well, in order for physical naturalness to provide a putative account of metaphysical naturalness, right or wrong, in order for it to even be the right sort of thing that we could compellingly say is a hypothesis about metaphysical naturalness, it has to fill analogous roles. So, for example, we need to be able to say something like, the more physically natural a property is, by the lights of the theory that posits that property, the more it makes for physical similarity and dissimilarity according to that theory. Or, the physical states characterized by a theory can't differ unless systems in those states differ with respect to the instantiation of the most physically natural properties of that theory. So here really in the supervenience, the sort of analog supervenience condition, what I'm saying is you can't vary the state of a system. You can't change how you represent a system according to the kinematic structure of the theory without thereby changing which judgments about property instantiation that theory makes for that system with respect to the most physically natural properties of that theory. We might then further say that the laws of physics, as they are perspicuously articulated in the native language of some formalism, should only refer to the most physically natural properties of that theory, something to that effect. And of course, there's then going to be disagreements about what the most perspicuous articulations of the laws of some theory happen to be. But nevertheless, this seems like the sort of appropriate analog of the laws condition. And lastly, we want to again insist on a minimality condition, whereby there's no proper subset of the most physically natural properties according to the theory, which likewise fill all of the other rules. Now, this minimality condition is really important in the context of physics, where we have mathematically sophisticated ways of kinematically representing properties posited by the theory. Why is this? Because when I've got a sort of rich mathematical structure that I use to kinematically represent properties, I can use that mathematical device to define some properties in terms of others. For example, the property of position and the property of linear momentum are such that if I take their cross product, I get the property of angular momentum. Now, angular momentum is thereby defined in terms of position and momentum. I can't change the instantiated value of angular momentum without changing the instantiated value of position or linear momentum. Now, because of this, there's reasons to think that you can't have all three of those properties be among the most physically natural properties of classical mechanics. There's redundancy. There's redundancy in the way that we've represented them kinematically. And so a big part of figuring out what the physically natural properties of the theory are amounts to eliminating that kind of algebraic redundancy. Okay. So I've now said several things about some necessary conditions for saying what a physical theory recommends as the most physically natural properties. And the whole point of doing this is that in order for physics to inform us about metaphysical naturalness, it has to offer some such recommendation. So now the question is, can we actually find such a recommendation within some mature physical theory? And the theory that I'm going to use as a case study is quantum mechanics. So there's some qualifications that have to be made here before I get into this, which is, I'm at a metaphysics conference. A lot of people at metaphysics conferences know something about quantum mechanics, but usually what they know about quantum mechanics is expressed in terms of state vectors on Hilbert spaces. In order to address this question, I'm actually going to need to make use of some more sophisticated mathematical machinery. So in particular, I'm going to need to talk about C-star algebras. I'm not going to explicitly talk about C-star algebras. There are some mathematical facts that I'm going to rely on in the argument that's going to follow this. But the details of those I'm happy to talk about at the end. I'm just going to gloss over them in the actual talk. But the reason for focusing on sort of more abstract C-star algebraic presentation of quantum theory is that there are a lot of physical systems of foundational interest, things like relativistic quantum fields or many-body quantum systems in the thermodynamic limit, which simply cannot be adequately represented using state vectors on Hilbert spaces. You need the more abstract, richer mathematical formalism of C-star algebras in order to express salient features of those systems. And since I'm talking about fundamental metaphysics, I need to be able to talk about the kinds of systems we take to be physically the most fundamental ones. So I kind of need to use this more sophisticated mathematical machinery just to sketch how it works. A C-star algebra is basically a generalization of the operators acting on a Hilbert space. There's a sort of robust mathematical sense in which those things are related to each other. And quantities are represented by self-adjoint elements of a C-star algebra. Determinate values of those quantities are then represented by the numerical values in the spectra of those algebra elements. These are basically like eigenvalues. And then the possible states that a physical system can occupy are represented by things called state functionals over a C-star algebra. And these are, in a precise sense, a generalization of density operators or state vectors. There's some details to figure out how that relation works, and it's non-trivial. But this is basically the way that you generalize the notion of a state vector to the C-star algebraic setting. Okay. So this is sort of a very rough gloss on the kinematic structure of quantum mechanics, articulated at a fairly high level of generality. I now want to sort of explore these kinematic posits. So I'm not worried about dynamics. I'm not going to be worried about the measurement problem. I'm not going to be worried about any of that stuff. This is just some basic kinematic constructions for how you build up the representation of properties according to the theory. I now want to know what viable hypotheses we can find for what the most natural of these properties actually are. So there's a first view that might strike a lot of people as sort of prima facie compelling. And the way to see this view come out is to first observe that with some small qualifications, self-adjoint elements of C-star algebras, brackets, strictly speaking, they have to be von Neumann algebras, can always be decomposed into a special subcollection of elements, namely the projections. So this is the spectral theorem. It's a famous result, and it establishes that all of the things that we take to represent quantities can be re-expressed algebraically in terms of a very small subset of those things, namely the projections. So this suggests that projections might be a plausible candidate for the most physically natural quantities. Give me any quantity that can be represented in the quantum mechanical formalism, I can decompose it in terms of projections. So it seems like projections are a really good way of eliminating all this algebraic redundancy that stands in the way of the minimality condition. Okay, so that seems like a plausible account that one might want to endorse. And there's other motivations for this kind of view. So if you are familiar with the quantum logic program, in that framework, people take projections not only to represent all of the quantities of quantum theory in a certain sense, but they actually take them to express all of the propositional content of the theory. And so in that respect, projections are really playing this like really overpowered role in how quantum logicians conceive of the contents of quantum mechanics. Similarly, if we go to a kind of quantum state monist position, according to which the only element sort of in the fundamental ontology of quantum theory is the quantum state, if you're something like a wave function realist, then it seems like the most fundamental property might be something like what quantum state the universe happens to be in, something like that. And there's a way to code those up if you're talking about state vectors on Hilbert spaces using what are called rank 1 projections. So the property of being in a particular vector state corresponds to a projection onto that vector state. So there's kind of a way of coding up the property of what state a system is in using rank 1 projections if we're talking about Hilbert spaces. So all of this sort of suggests a view according to which the most physically natural properties instantiated by quantum systems are those that are represented by some collection of projections. So I take it that this is a view that lots of people would sort of take as their first gut reaction to the question of what are the most natural quantum properties. But there's reasons why it can't succeed. So first, in order for these sorts of views to succeed, in order to say that the most natural properties of quantum theory are represented by projections, you need to be able to find a minimal collection of projections, a collection of projections which suffice to generate all of the other quantities represented in quantum formalism that can't be stripped down any further. Now, it's a mathematical fact that in basically all C-star algebras that are not the ones that you find exactly in the Hilbert space setting, you can't do that. So it's a mathematical fact that for anything that's what's called a non-type 1 von Neumann algebra, which is effectively all of the algebras that represent realistic physical systems, there are no minimal projections. So things like rank 1 projections are really special. They're a really special feature of the Hilbert space formalism, and you don't get them in most other settings. And so we can't actually find a minimal subcollection of projections that generates all of the other self-adjoint elements of the algebra in a way where there's no internal redundancy among the elements. So you can't satisfy the minimality requirement if you restrict yourself only to projections when you try and answer the question of what are the natural quantum properties. Now you might say, okay, well, this is sort of an artifact of being in this really abstract mathematical setting, but there's a more straightforward reason why this account can't work, which is that projections don't generally appear in things that we call the laws of quantum mechanics. Or if they do, they certainly don't appear in all of them. That is to say, the laws of quantum mechanics seem to refer to loads of properties that are not represented as projections. Take, for example, canonical commutation relations, the Schrödinger equation, the statement of any kind of Lagrangian, the Euler-Lagrange equations, anything like that you might want to call a law of quantum mechanics. Those sorts of things refer to all kinds of properties that are not represented by projections. Hamiltonians are generally not projections. Now, this is a reason that the laws condition can't be satisfied by a projection-based account. So the conclusion is that this sort of first pass, this projection-based account of natural quantum properties, it fails. It's not a tenable account. So let's move to a different possible way that we could proceed. So another view is that some quantities, so it's true that some quantities change their values under changes of coordinates, or more broadly, under symmetry transformations. So there are quantities, I can write down the position of something. If I change my coordinate system, the value of that quantity is going to change, right? But we think that coordinates are kind of merely representational artifacts. They don't really track features of the thing we're trying to represent. They're just devices that we use to represent those things. So for this reason, you might think that only the symmetry invariant quantities can be the most physically natural. Only the quantities whose values don't change under symmetry transformations can count as the most physically natural quantities. Now I'm very intentionally not saying what I mean by a symmetry here, because there's loads of different notions that one could fill in there. But what's true of all of them is that if they can be implemented by some sort of group action, then this account also can't work. Okay, what do I mean by this? So first of all, here's the account that's now on the table. According to this sort of symmetry-based account, the most physically natural quantities instantiated by quantum systems are those which are invariant under the symmetry transformations associated with those systems. Why do I say that this view can't work? So, first problem, symmetry invariant quantities of some C-star algebra, the self-adjoint elements of a C-star algebra that don't change under the action of some symmetry group, those also form a C-star algebra. They form a sub-C-star algebra of the first thing. Now, because they form a sub-C-star algebra, you can add them, and you can multiply them, and you can take scalar multiples of them, and you can take convergent sequences of these operations of them, and still end up with other symmetry invariant quantities. This means that, once again, we've got this redundancy that we were trying to eliminate via the minimality condition. And so, because symmetry invariant quantities form a C-star subalgebra, because you can add them together, multiply them, and generate new symmetry invariant quantities, we can't satisfy the minimality condition with them. Now, we run into another problem. So in a sense, there's too many of them. But there's also, in a sense, not enough of them. What do I mean by that? Well, if you define a quantum state over a subalgebra, you can't uniquely extend that to a state over the entire algebra. In general, there's actually a lot of mathematical complication to this claim, but generally speaking, if you write down a state functional and you specify its values for all the quantities in the subalgebra of some algebra, you can't thereby uniquely extend that to a state over the entire algebra. What this means is that the supervenience condition also can't be satisfied. If we take physical states as representations of states of affairs, you can't change which state of affairs you're representing, you can change which state of affairs you're representing without changing the way in which symmetry invariant quantities are instantiated. So we can't uphold supervenience with these kinds of quantities. So once again, we have an account on the table, but that account fails. We can't actually use this account. So I've now given two kind of what I take to be fairly intuitive accounts of what the natural properties of quantum theory would be, and basically shown that actually the formalism of quantum theory is really sensitive, and these sorts of naive ways of approaching the problem are not actually viable. So the question of what are the most natural quantum properties is actually kind of a hard one to answer. Now, I'm going to put on the table a positive view that I think can work. I'm not convinced that it's the one true correct answer, but it's something that can work, just to sort of sketch how such a story would go. And the way that I'm going to motivate this view is to say, well, for both of the last two accounts that I considered, I just said, consider a C-star algebra. But in this case, I think a better place to start is to first ask, how is it that we decide which C-star algebra is appropriate for representing which quantum system? So we don't just get handed from God a C-star algebra and told that represents electrons. That doesn't happen. We have reasons for picking particular algebras for representing particular systems. And those reasons, I think, play into how we should pick an account of the most natural quantities that appear in those algebras. So how do we figure out what algebra to use? Well, we generally generate algebras using some kind of quantization procedure. Now, there's loads of different ways of doing this, and I really don't want to go into any of that, but roughly speaking, it's sort of in general, the way that proceeds is you first stipulate the existence of some quantities that you stipulate stand in various relationships to one another, such as canonical commutation relations, or canonical anti-commutation relations, and so on. So you say, I stipulate there exist these quantities, and they are related to each other in these ways. And then, having done so, you generate a C-star algebra from those, according to some prescription. And there's lots of different ways of specifying what that prescription is, but the idea is that you first start off with a stipulation of there exist some quantities, they stand in these relations, and from those you build all the rest. So I think that this suggests a fairly natural quantization-based account of physical naturalness, according to which the most physically natural quantities instantiated by quantum systems, represented by a particular C-star algebra, just are those quantities that appear as the sort of self-adjoint generators of those generating algebraic relations. The ones that you posit in the first instance and say, there exists a property X, there exists a property P, and the commutator of those is equal to IH bar times the identity. those things, I take, are the things that we should think of as being the most physically natural quantities appearing in those algebras. So by design, the elements appearing in these generating algebraic relations suffice to generate the entire algebra. And so supervenience is in fact satisfied. This is kind of the whole point of what quantization is supposed to get. Okay, but if we, and this is sort of more of a speculative claim, if we think that things like canonical commutation relations or canonical anti-commutation relations, if we think that those algebraic relations are used to generate the algebra have a kind of gnomic status, if we can treat those as laws, even if they're merely laws of physics and not, say, laws of nature understood in the manner that a metaphysician would want us to understand them, then clearly all of those generating postulated quantities appear in the laws, and so the laws condition is satisfied. The laws refer to them, but moreover, minimality is also satisfied because you couldn't state the laws without referring to those things. So they're all necessary. They generate the entire algebra, so they're all also sufficient. So for these reasons, I think that this account is a tenable account of what the most physically natural properties of quantum theory actually are. I could be convinced that there are problems with this account. There's some I already consider, but I think that this is sort of a good first pass, and I'd be really interested to hear if anyone has good knockdown objections to this or suggestions for better alternatives. So to summarize kind of the main takeaway of this whole talk, the first thing that I did was I articulated some necessary conditions that would be required in order for physics to inform us about metaphysical naturalness in the way that naturalness theorists often suppose. Naturalness theorists say physics tells us about what the most metaphysically natural properties are. They don't tell us what those properties are. You really need to appeal to the internal structure of how physical theories represent things in order to be able to make good on that claim. So then the question is, how do we do that? So I distinguished physical from metaphysical naturalness, and I laid out some conditions that have to be satisfied in order for that project to be tenable. You might not find those conditions viable, but that's more a problem with finding the project viable rather than the particular deployment of it. I then showed how these necessary conditions constrain what the most physically natural quantum properties can be. In particular, I went through two, I think, fairly intuitive accounts, prima facie intuitive accounts, and showed that actually for fairly sophisticated reasons, mathematically speaking, they are not appropriate for filling this kind of role. It's actually very difficult to find an account that meets all the relevant criteria. And then I defended a positive account of natural quantum properties, which, depending on your intuitions, deviates from what some people might initially expect. And so the upshot is basically that we can't just naively say, physics tells us about the metaphysically natural properties. You actually need to do a lot of work to dig into the core details of how physical theories represent their subject matter and pay really close attention to the mathematical framework that they use to do that in order to be able to say that. And that's actually not a trivial thing to do. So that's basically what this has all been about, and I'd be very happy to hear any comments that you guys might have. So thank you very much.
Thanks, Patrick. Now we have Cristian López.
No, it's fine. Okay, good. First, no, it's not working.
It was working, just unplug it and plug it back.
Okay.
Just like the...
Yeah. Here. Good. Okay. Now it's fine. Okay, first, thank you very much for the talk and for the presentation. I am not quite familiarized with the discussion on this topic, so maybe my comments are guided by intuitions or some maybe clarificatory questions. I have 4 comments. Let me go to the first one. Is this relation between physical and metaphysical naturalness? This is the first part of the presentation, also the first part of the paper. You refer to that as physical naturalness approaching or converging to metaphysical naturalness. My worry is how this framework is supposed to work. This is not working. Yeah, it's working now. How it's supposed to work in the following sense. I imagine that if we are naturalists, right, then we come to know what is metaphysical naturalness through physical naturalness. So this is what the ideal is supposed to be. So because by intuition we don't believe that there is an independent means to get knowledge of metaphysical naturalness if it's not through the physical naturalness. So, but then how do we know exactly that we are approaching metaphysical naturalness or that physical naturalness is converging to metaphysical naturalness, right? It seems that there are two assumptions here by this idea of converging or approaching. One is that indeed we have an independent knowledge of metaphysical naturalness. I mean, we need to specify which is the structure of reality independent from physics, and then we can say, okay, this thing is approaching this other thing because we already know it. But this is not quite naturalist. But also it's supposed that we can see the relation externally, right? When we can stand out of the relation and say, okay, these two things are approaching. But in the naturalist framework, it seems that we don't have this external view. We are always within physics trying to learn about the world. Of course, you can say, well, fair enough. Metaphysical naturalness is nothing but physical naturalness. Yeah, I mean, I think this is the approach that if you're a naturalist should follow, but then my question would be, why do you think that the metaphysical criterion for metaphysical naturalness are also valid for physical naturalness? Maybe they are not. Maybe you can have other criteria for physical naturalness. Or you can say, no, we are not naturalists, like me. I don't believe that naturalists is a good position. But then we don't care very much about the relation, right? I mean, the relation, I would say physics is revisable, it's fallible, full of determination by data. And I like metaphysical naturalists to be more stable, right? So, yeah, I mean, you have these two views, and for me, there's the kind of dilemma that we are facing here is that either if you go completely the naturalist way, where, okay, maybe you have to think about the criteria because probably they are not the same. If you are not non-naturalist, then the distinction is not very useful. So this was my first comment. Maybe you can comment at the end. The second is on supervenience, star, and minimality. This is for physical naturalness. This is a quote for your paper that you kindly sent me. You say that in order to satisfy minimality and supervenience, the most physically natural quantities posed by a given theory must therefore be a distinguished collection of the quantities kinematically posed by the theory which generate the rest. This introduces the additional challenge of determining which of potentially many minimal subcollection comprises the most physical natural quantities of the theory. That's fine, and this is probably the best way to put it. My worry is that I think it's not so easy to get. First, probably this is more ideological, I don't know, but most physical theory can give even different formulations. And at the same time, as you are dealing with CSR algebra, you can also give different inequivalent representations of the CSR. And also different interpretations, right? And at this point, it's like, okay, you can select a subcollection of quantities, but then this is going to be formulation relative, this is going to be relative to the representation, also relative to the interpretation. So it's like you have a huge leeway, and then, okay, we need to rely on another criteria to select which is the most valid thing. And related to that is that when I believe that physics by itself, I think that you mentioned it in the presentation, there's nothing about which are the genuine properties, right? You need to do something else, and you need to rely on external criteria. And this is what, when I was reading your paper, I was thinking of maybe there's this risk of falling into what has been called the naive realism about operators. And this is something that I think that Bowmians have raised, and I think that they are okay, even you can buy or not the Bowman story, but I think that they are quite right in saying that, okay, when you have an operator, you don't have to believe that all the operators are going to refer to something. You need to do something else. You need to somehow select, rely on some external criteria to say, well, okay, these are the operators that really represent properties. Maybe the others are not representing properties, they are representing something else, playing some role in the theory. So, again, I couldn't see in the paper if you have thought of something like that. If you have some criteria to say, okay, well, okay, yeah, this is the way in which I'm going to avoid this naive realism about operators. In the sense that, well, probably we shouldn't take too seriously the representational means of the theory. Okay, which one is within my question? And finally, about C-star algebra. I have here small comments. As I see in general, this is just language that we know. The physicists can choose for explaining, to model a system, but it's not clear for me why they are so metaphysically important. Right? I mean, I think that something else, I would ask something else to say, okay, why C-star algebra? Why not more general formulations that C-star? I mean, C-star algebra is one way to go, but you have others too. Why they are so metaphysically important? Because prima facie, they are just a language. We have, as you said, a powerful they have a very, very strong expressive power. And now this is probably this is not something I'm not very sure about, or maybe you can correct me, or anyone in the audience can correct me. But I'm not sure if exactly C-star algebras are playing the role that you want them to play. And this is what I think I know about this is that, okay, the algebra by itself is just formal. Then you need to introduce some physical content into the algebra. You have many ways to do it. One way is to realize it completely via the Hilbert space representation, right? Then you have some physical meaning in the Hilbert space representation that you can introduce, for instance, by the symmetry generators of the group, and then you can translate this into in the algebra. Fine, this is one way to go. But I think that is a problem because even for a single C-star algebra, it can have many inequivalent representations of Hilbert spaces. And this is something I'm not sure about, but I think that I learned somewhere. If that is true, then one algebra, it has multiple ways can manifest physically. And sometimes different representation of the same algebra correspond to different physical systems. And this is something good because algebra has this expressive power that you want to talk about families of models and not just isolated models. So it's a virtue of the theory to be general, to be multiple, realizable in different, physically in different ways. So this is more or less the argument as I thought about it. That C-star algebra doesn't, in general, determine a unique physical system on its own. The physical interpretation depends on which representation, which state of class of state is chosen. In general, if you want to put it in a stronger way, we say that the algebra alone is underdetermined. And this is the virtue of the algebra, that we can represent a family of physical systems by introducing some boundary conditions, etc. The question is, okay, we have the C-star algebra, this story, but if we have this expressive power so nice that we want to have, I don't see how we can get natural properties from something that is looked to me is a bit general. And finally, I think this is my last comment is about, in your proposal quantization, you talk about laws, and you said that laws is satisfied by the canonical commutation relation. And this is probably just a clarificatory question is why it is a law. I mean, prima facie it doesn't seem to be a law because it sets the arena for the kinematically possible state, right? But it doesn't tell us anything about how the system is going to evolve. It doesn't tell us how to select the Hamiltonian that's going to govern the evolution. We cannot make prediction with that. We can say almost anything about how the system is going to evolve. So it says, okay, maybe in the standard ways it doesn't look like a law. Maybe it's a law if they say, okay, think of the best system, this is an axiom in the best system, then it's a law. Okay, fair enough, but you have to say it somewhere. I think that's everything, so thank you.
Could you read this up, actually? So,
Here or back? Here or back?
just here.
Okay, yeah, perfect.
So, if I've got a couple minutes to respond to that. So, I'll start with the C-star algebras, some of the C-star algebras. So there's a lot of, I'm not going to probably respond to everything you said.
Don't worry.
Yeah, but, so the first thing is that, okay, I basically have two main comments about C-star algebras that I think are quite relevant. So first of all, you seem to be suggesting that you can't interpret a C-star algebra and the state functionals over it on their own as having physical content. You have to give them a Hilbert space representation, and that's somehow where they get their physical content from. And then somehow C-star algebras are just like a merely formal language, and whereas Hilbert spaces are the physical thing. Now, my pushback on that is Hilbert spaces are just as abstract, just as mathematical as C-star algebras. So you can say my C-star algebra represents quantities and the state functionals represent physical states of affairs, or you can say density operators on a Hilbert space and self-adjoint operators on a Hilbert space represent properties and states of affairs. But in both cases, you still are going to be relying on some sort of relation that links up a collection of mathematical objects to the thing that they're supposed to stand for. And so I don't think that there's any problem faced by C-star algebras that's not also faced by Hilbert spaces. And I think it's just standard practice in physics to use mathematical machinery to describe physical goings-on. So I'm really concerned with a way of characterizing these things. There are other ways of characterizing things, different theories as well, but ultimately I don't think that you need a Hilbert space representation in order to imbue the theory with physical content. Second claim to that effect, it's true that there are unitarily and equivalent Hilbert space representations of the same C-star algebra. This is a very famous fact. There's been lots of philosophical discussion about this. However, it's not the case that they give disagreeing physical descriptions of the same system. What they do is they allow you to represent different parts of the same C-star algebra. Here's what I mean by this. If you consider all of the states over a particular Hilbert space, over a particular C-star algebra, and you pick out irreducible faithful Hilbert space representations, what you'll end up with is a situation whereby the state functionals that can be nicely paired off with density operators on a Hilbert space under one representation are disjoint from the state functionals that can be lined up with density operators under a unitarily inequivalent Hilbert space representation. So the folia of state functionals are disjoint. So you can use a particular Hilbert space representation to give a nice sort of pictorial image of what's going on for a particular subclass of states on a C-star algebra. But you can't do that for all of them at once. So Ritchie, for example, has some nice stuff about KMS states. In equilibrium quantum statistical mechanics, you basically can't have more than a single state represented on a particular Hilbert space that is an equilibrium state. You kind of only get one temperature that you can possibly have equilibrium at on a given Hilbert space representation. So if you want there to be more than one temperature at which there can be equilibrium, you need to use inequivalent Hilbert space representations, and states that satisfy the KMS condition, I think, have to be mixtures of states that are representable on different Hilbert space representations. So you really need the C-star algebraic structure in a way that you can't just extract out of the Hilbert spaces. I think that Hilbert spaces play an important representational role in quantum theory, but I don't think that you actually need them in order to just say what the properties are and say what the states are. You need to use them in order to tell a more compelling story about dynamics and things like that. Okay, there's lots more to say about that, but I'm going to not do that. Instead, I'm going to go to the first point. So you were putting pressure on the idea that physics can inform us about metaphysical naturalness, and what the convergence would have to consist of. And I think that that's totally right. So my big qualm, the thing that sort of set this whole project in motion, was reading a bunch about naturalness and seeing kind of without fail, every single author who talks about it says, and physics somehow tells us what the natural properties are. And there is actually a whole literature of people being skeptical of the possibility of this happening. So with von Frossen and Barry Lower and Cohen and Callender, there's all these things where people basically say, like, look, if we want to try and use, I mean, they're mostly concerned with laws of nature, but if we want to use natural properties to sort of underwrite an account of what the best systems of laws of nature would have to be, you run into some really weird skeptical challenges. So let's suppose, contrary to all of the scientific anti-realism debates, that we've arrived at a final theory of physics that's perfect in every respect, but we just happen to express it in a not perfectly structural language. It has the wrong predicates. You can define all the perfectly natural properties in terms of its predicates, but the language we actually articulate it in is somehow, not the most structural language. Then, if you run your sort of best systems calculus to determine what the simplest, most informative axioms of the theory would be, you'll end up with a collection of things that won't refer to the most natural properties because you're expressing them in a language that doesn't have predicates for those. And so, there's reason to think that even if we overcome scientific anti-realism issues, we still shouldn't expect physics to converge on the metaphysical joints. And it's really just like a matter of, it's a matter of historical contingency what language we use to express our physics. But the people that have these objections to the possibility of physics informing us about metaphysical naturalness, the way that they all get out of it is by saying, okay, so let's ditch metaphysical naturalness. Let's just let our theories do all the work. What we should count as a law of nature is like what is natively expressed in the language of the physics that we're using. So really what they're doing is like replacing metaphysical naturalness with this thing we have epistemic access to, which is physical naturalness, qua an internal feature of our theories, which might well hit the world. And in fact, a lot of people are like totally skeptical to the idea of there being metaphysical naturalness at all, right? So like Goodman being a famous example, people who think there is no standard of objective similarity out in the world. There are no metaphysical joints. Nevertheless, people of that sort would still agree that there's some sort of like conceptual or cognitive or inferential relevance to how we order the properties that appear in our discourse. And some properties appear to us, maybe they're better entrenched or more psychologically salient or something like that. There still is some kind of property, some sort of ranking among properties that fills these kinds of roles, even if it doesn't do so as a feature of reality, but rather as a feature of how we characterize reality. And so I fully agree, there's reasons to worry about physics telling us about metaphysical naturalness, but I think in asking the question, you still end up in an interesting place where you say, okay, to answer that question, we still have to sort of fold the notion of naturalness inside of the formalism of our theories. And kind of everybody has to do that if they want any analog of naturalness whatsoever. But once we do that, that's really all that we need. But then it's still actually really hard to say what that ranking concretely turns out to be. And so a big task for this project was basically to say, okay, it's like really not trivial to say that physics converges on the metaphysical joints, but it's also not trivial to say what the physical joints are. And trying to spell out what that looks like is itself rather difficult. I might say just one more thing. So the naive realism about operators. What I've done is I started off by saying, here's how a particular theoretical framework posits a collection of representational resources that are supposed to stand as names for properties. And when we do physics, that's what we do. We say, here's how I'm going to mathematically represent a bunch of properties. Here's the rules that are going to tell me how they're related to each other. Here's the rules for how I'm going to say what it is for a system to instantiate those properties and so on. And you can't articulate a physical theory without doing all of that stuff. And if you change your choice of how you've done that, you end up with a different theory. So in Bowian mechanics, for example, you specify a different collection of quantities. It's a different theory, kinematically speaking. You've got different states, you've got different quantities. It's not, kinematically speaking, quantum mechanics anymore. Now, there's interesting relations between Bowian mechanics and quantum mechanics, of course. And you could probably run a similar story in the context of Bowian mechanics. But really, I wasn't trying to be a naive realist about operators. What I was trying to do is to say, we've got this well-established recipe for constructing a formalism for a particular theory, let's see if we can ask these naturalness questions of that formalism. And it's pretty good formalism. It does a lot for us. You might want to try and do a case study with a different formalism. You might want to try and do an analogous thing for Bohmian mechanics, but that's kind of a different project. Yeah, I'll stop with that.
Thanks.
Okay. Yeah, thanks. I think I agree with your positive proposal. I worry that it undermines your project. You stipulate that actual properties are self-adjoint operators, the self-adjoint generators of your algebra. So various people have said that quantum theory is a theory schema or a framework. Right?
Yeah.
So you give me some properties, I'll tell you how to quantize them,
Right.
generate a quantum theory. So then it looks like you're feeding in the natural properties at the outset, and wherever you're looking for the natural properties, it's outside of quantum theory. Right?
Yeah.
So that's my worry.
No, I think that that's a really good worry, and I think that actually puts things in a way that I actually quite agree with. So, in the paper of this, as Cristian knows, I haven't really figured out exactly where it's going to end, and so sort of the current stage of the project is I've just been considering lots of different options, and my sort of main gut feeling is that actually it's kind of a fool's errand to try and do like the theory, I can just read off natural properties from the theory, but in order to sort of test that claim, I kind of had to try it out a few times. And the first few times I tried it out, it went badly wrong, and I thought, great, we're on the right track. And then I tried it out again, and I got something that met the conditions that I laid out, and said, okay, I got to back off a little bit now. But I think that you're probably right, that this is like, the way in which I was able to give a positive account sort of shows why a positive account can't be tenably given. So yeah, that helps a lot. Thank you.
Okay.
Go ahead.
I really like the project. I think you're doing good work. In the end, I think I'm very sympathetic to your proposal, at least for how we ought to investigate the question of what does quantum mechanics tell us about the natural properties. I want to make two friendly suggestions.
Please.
So the first is a reminder that metaphysics didn't start with David Lewis. So arguably this goal of identifying the properties that satisfy similarity, supervenience laws, and minimality goes all the way back to the basic graphics.
Yeah.
So like folks like Democritus positing atoms and void and such. Second suggestion, I think the question, what are the natural properties, is sort of ambiguous. And by the end it becomes clear that there are actually two very different questions we can ask. So one is something like this: what is it for a property to be natural? And the basic answer is, what's one of those that satisfies the four conditions? The other question is the one that scientists seem to be more interested in, which is, well, which properties are the natural ones? Like, how do we write down the correct theory, the correct equations? And so I think that if you just distinguish those questions right off the bat, it will maybe help to avoid certain kinds of pushback.
Okay. Yeah, that makes sense. Great.
I was wondering, thank you so much for the talk. So I was wondering about the method here, because it seems to me that you buy into the commitment or principle that laws of nature only refer to physically natural properties. But here, and usually in the literature of quantum mechanics, especially G. North, specifically refers to dynamical laws of nature. And I was wondering why here you start with a kinematic construction and not starting from laws of nature, dynamic laws.
Right. Good. No, that's a really good question. So, largely I focus on the kinematics just because that's the stage of theory construction at which we say what the properties are. It's kind of where we still have the most leniency, the most wiggle room. But you're absolutely right. Once we start talking about laws, you really should also be talking about dynamical laws. And so I left off some. So in the projection-based account, I kind of made a big deal out of the fact that projections don't really appear in the laws. So you can't state the laws only by referring to projections. But something that sort of is in the paper but not in the talk is, well, if you're doing this sort of canonical commutation relation business, that on its own isn't really fully enough, right? So of course, you need to impose these conditions in order to say, what the algebra is that you're studying, but you also need to say what the Hamiltonian is. And, obviously, if I'm looking at the free Hamiltonian, I can define that using momentum and some scalars. So, there's a sense in which, if I forget about dynamics, I might end up with far too small of a collection because I'll go, oh, that's redundant, I can eliminate it. So really to make, to give a proper account of these properties, you'd have to first give an account of what the laws of quantum mechanics are. I take that to be a fairly contentious issue that I don't really want to have to deal with too much. But it is true that when you impose canonical commutation relations and anti-commutation relations, that constrains a lot of your options about how you can articulate what the dynamics are going to look like. So I'm also inclined to think that just as we should distinguish between metaphysical naturalness and physical naturalness, we should probably also distinguish between the laws of nature understood metaphysically and the laws of nature understood as articulated in physical theories, for example. So, the language of C-star algebras and Hilbert spaces and all that stuff, that might not be, in the decider sense, the most structural language for carving reality, but in the physics sense, it kind of is. It's sort of the most perspicuous language that physicists use. And so, if we talk about, the laws of nature qua physics rather than the laws of nature qua metaphysics, we kind of get a little bit more room to just say, the laws are, whatever the equations are that the physicists write down, right? But no, I think you're absolutely right. Dynamics does play a role that I definitely have eschewed. Thanks.
There is my point about something you said earlier in response to Cristian. So you mentioned this debate of people imagining, okay, let's suppose we get to the final theory, and still the final theory doesn't, specify what the properties are. I think there's two reactions to this, right? And I want to hear what you think. The first reaction is, that's sad. Second reaction is, but maybe we had a very bad definition of what a final theory is. Right? I think some people, even now, may think that whatever final theory is going to be exactly the thing that specifies what the properties are. So it's, by definition, impossible that we get a final theory without it specifying the properties. And I think this applies for the final theory. But, some people may think that it also applies to the case studies that you're thinking at right now.
Mm-hmm. Yeah, so, okay, this is good. So I think that, so people who want like a capital M metaphysical conception of naturalness sort of need to be open to the idea that, right now in history, we're in a situation where physics is probably not fully comprehensive, but if we want to know about the metaphysical stuff, we might want to hope that someday we get there. Now, the requirement for convergence is not just that it gets all the facts right, but that it gets all the facts right expressed in the right language, which seems to be kind of a strange imposition. You could, of course, then say, well, a final theory is not just a way of characterizing a bunch of facts, but it's a way of characterizing a bunch of facts in an appropriate language. So that's definitely an option. But the other thing that you can do, and this is, so this is all supposed to be framed as a response to a very particular kind of way of doing metaphysics. But another option is to take kind of the Persian line and to say something to the effect of, well, what could you possibly mean by metaphysical naturalness? If not, what would be most natural according to the theories we arrive at the end of inquiry? And if you take that kind of line, then there is simply nothing for metaphysical naturalness to be other than the thing to which physical naturalness converges. And that's a live option. It's just not one that the debate I'm trying to situate this all in is really receptive to. Yeah.
I have a really good question. You alluded to the right language, and I'm curious if you take that to be something that is line independent.
So it depends on how you think of reference, broadly speaking. So if you, with David Lewis and Ted Sider, think that reference is magnetic, then you think that, you know, there's a sense in which we are disposed to referring to nature along its most natural joints, in which case the languages that seem, you know, perspicuous to us for carving the world up are also metaphysically perspicuous in some way. But if you don't find that kind of view compelling, then, yeah, I think according to someone like Sider, there is like a metaphysically favored language. It's like the language whose quantifiers are all and only the most structural quantifiers, and whose predicates name all and only the most metaphysically natural properties, and whose you know, proper names label all and only the most basic entities out of which everything is mereologically generated, and whose relation, it's a ... right? There's like the metaphysically favored structure. Anything that names that kind of structure appears in the metaphysically favored language. We might get really lucky and like find a fragment of that language, but we might not. I think Sider thinks that we would, or that we are kind of in a position to think that we've got access to some part of that language. Okay, let's then go up.